Okay, we are now recording. If I can get okay. Evidently, every time I tried to open, then it finally did open, and now I'm having to close them all. Okay, good. Finally. Wow. Okay, let's get this slideshow set up. Boy, the computer, I guess, is just incredibly slow. I guess that's what the problem was. I don't know. Okay. We're recording. We finally got it up. It's going. Let me go over the last few announcements. I guess I'll take them in chronological order, though that doesn't seem like it. Next Tuesday, I have a doctor's appointment. I found out it is at 8 o'clock. I have to be in for labs at 7. He only sees patients on Tuesday morning, so I can't get out of it. So, we will not have class next Tuesday. But when we talked about it 2 days ago on Tuesday, some of you said you could come today at 12:30. Is that still on? Not. Nobody? Okay. Can anyone come today at 12:30? Okay, how about next Tuesday at 12:30? Possibly? Okay. Okay, but not today. So you want to move it to next Tuesday at 12:30. Okay. So we won't meet today at sorry, at 12:30, but we'll try to meet next Tuesday at 12:30. Don't show up at 8. I will not be here Tuesday, okay? But show up at 12:30 if you can. If you can't, I'll be recording on Screencast-O-Matic, so it'll get out on YouTube. All right. With that said, then, today I'll probably try to make up my differential equations class. Now, we probably won't start at 12:30. We'll probably make it something like 1 o'clock or something like that, maybe 1:50, something like that, so we'll have a chance to eat lunch because there's only a few students in that. So I will let them know this morning. My linear algebra class, I think we'll meet next Tuesday because I hope I'll be back by then. All right, the other next thing, tomorrow, normally I'm on Birmingham campus for office hours, 7:45 to 11:45. Not tomorrow. I've got a treatment tomorrow. I've got to be at labs at 6:30. Treatment starts around 7:30, and it'll probably go 7 hours or so. So the odds are definitely not going to be on campus all day tomorrow. And guess what? Not going to be on campus next Friday either. Nor will you, because it's Veterans Day. Okay, so next Friday the campus is closed, state holiday. Which brings me to one other change in office hours. Next Thursday, 1 week from today, we have a faculty meeting at 2:30 over in the Ethel Hall building on this campus. So that means my office hours are shortened that day. Normally they're on Thursdays, they're 12:15 to 3:15. Then next Thursday will be 12:15 to 2:15. Today will probably be 12:15 to 1 or 1:15, something like that, and then something like 2:15 to 3:15. So they're all screwed up these next 2 weeks. All right. Any questions? Especially about math or any other thing. Okay, we're in Chapter 2, Section 2.3. Chapter 2 is polynomial and rational functions. 2.3 is polynomials and synthetic division. And now we're going to do remainder and factor theorem, the last couple of items in this section. Now, the remainder obtained from synthetic division process, and I think I already told you this, has an important interpretation. I showed this to you on an earlier one. It's described here in the remainder theorem. If a polynomial f of x is divided by x minus k, which kind of division can we use if it's x minus k? kind of division can we use if it's x minus k? Synthetic division. You can always use log division, but if you got a divisor, x minus k, in other words, coefficient of 1, exponent of 1 for your x, then you can use synthetic division. But whichever you use, long division or synthetic division, when you divide the f of x by x minus k, the remainder is, that r remainder is f of k. In other words, if you had taken this k, actually the opposite of whatever this is, that k, plugged it in here, then you get the remainder is your f of k. Pretty amazing, okay? The remainder theorem tells you that synthetic division can be used to evaluate a polynomial function. Sometimes if it's a really hairy, messy polynomial function, rather than substituting in big numbers and raising them to big powers, just do your synthetic division, because synthetic division is just dividing, multiplying, multiplying, adding, multiplying, adding. That's all there is to it, and they're usually fairly simple numbers, okay? So that is to evaluate a polynomial function, f of x, when x equals k. Notice, if you set this equal to 0, then add k, you get x equals k. Divide f of x by x minus k. In other words, when you're evaluate a polynomial function at a value, divide what would have been if that was a factor, and it's not, but the factor that represents that value, okay? The remainder will be f of k. And that's what example 5 is going to show. Let's do it. Use the remainder theorem to evaluate f of x equal 3x cubed plus 8x squared plus 5x minus 7. How would you do it when x equals negative 2? How, said the chief. Okay. What would you do? There's two routes you can do to evaluate. The easy and the hard, huh? Synthetic division. So what would you put where? Okay, let me get Mari here. Second. Okay. Okay, you put negative 2 outside the house. Let me get my black pen activated. Okay, negative 2 outside the house. 3, 8, 5, negative 7. Okay, then what? Skip a line, draw a line. Then bring the 3 down. Okay, now what? Multiply, and that gives you. And then? And what that gives you? Then? And that gives you negative 4, 1, negative 2. Is that what you said? Negative 9. Okay? Do you believe that f of minus 2 is equal to negative 9? That's what the remainder theorem tells. You do the synthetic division, and notice, pretty simple to do, okay? Then you get negative 9. Let's check it and see. Let's plug in f of negative 2. What would that be? 3 times. Plug it in, plug it in. Say again. I thought I heard someone say it. Negative 2 cubed, folks. A little louder. Negative 8. Good. Okay. Plus 8 times. Help me. 4. Good. Okay. Plus 5 times. Negative 2. Well, I forgot my 5. 5 times negative 2 minus 7. Okay, let's see what we got. 3 times negative 8, negative 24, plus 32, minus 10, minus 7. All right? Let's do the minuses first. That'd be minus 34, minus 41, plus 32, minus 41 plus 32 is, well, pull out those black boxes, okay? Can't take that long, can it? Negative 41 plus 32. Huh? I'm sorry? Okay. What you got? Negative 41 plus 32. Negative 9. Very good. And that, sure enough, is your remainder. Okay? Now, which was easier? Synthetic division or multiplying all those together? I think synthetic division was easy. Those are simple multiplication, subtraction. That's all you do. Over here, it's raising the powers and then adding signs and all that kind of stuff. Especially when this number gets bigger and bigger and these exponents are pretty high, you can have a mess, okay? But synthetic division, generally your numbers are fairly simple and small, okay? Any questions on that? All right, to erase it. Okay? All right, let's see how they did it. Using synthetic division, they put the negative 2 on the outside, the 3, 8, 5, negative 7 inside. Yes, they draw their boxes differently. Skip a line, draw a line. Bring down the 3. Negative 2 times 3 is negative 6. 8 minus 6 is 2. Negative 2 times 2 is negative 4. 5 minus 4 is 1. Negative 2 times 1 is negative 2. Negative 7 minus 2 is minus 9. I like to separate that off to remind myself that is my remainder. That is the functional value. Okay? Because the remainder, R, is negative 9, we can conclude that F of negative 2, whatever was on the outside here, is the answer there, remainder there, negative 9. Any questions? That was example 5. They do have a checkpoint, and they have 4 that you can check on there. I would definitely do some of those just to get it down. Okay? This means that negative 2, negative 9 is a point on the graph. You can check this by substituting x equals negative 2 in the original function. We already did that. So this gives you something else, doesn't it? When you're graphing a function, rather than having to plug in values and calculate, especially if it's a pretty complicated function, just do synthetic division with different numbers over and over, and you can get your points. Whatever you put on the outside here, that's your x value. The outside there is your y value. Okay? And here's how they checked it. F of negative 2 is 3 times negative 2 cubed, plus 8 times negative 2 squared, plus 5 times negative 2, plus minus 7. And that's 3 times negative 8, plus 8 times 4, minus 10, minus 7. Sure enough, minus 24, plus 32, minus 10, minus 7 is minus 9. They did a little quicker than y'all did. Never mind. Okay. Now, another theorem follows from that is the factor theorem. And here's how it's stated. A polynomial f of x that has a factor x minus k if and only if f of that k is 0. Okay? Now that follows because you see the remainder of this, if you divided this into that by our last thing, would have to be 0. And if that remainder is 0, that means that's a factor. Okay? So sure enough, we have, and this is sort of what we've been building toward, now we have another way to factor big, hairy, messy polynomials that none of our other techniques will do. The factor theorem, synthetic division, helps you factor those. Using the factor theorem, you can test whether a polynomial has x minus k as a factor by evaluating the polynomial x equal k. That sort of does it the other way. If it's real easy to plug in x equal k here, if you do that and get f of k is equal to 0, you know x minus k is a factor. You know it, okay? If the result's 0, x minus k is a factor. Make sense? All right, here's example 6. Show that x minus 2 and x plus 3 are indeed factors of that polynomial. Is there any way you could have factored that using techniques we know already? You can't use factoring by grouping for several reasons. One is it's an odd number of terms. Can't do it, okay? So we don't have any tools in our tool belt to factor that. But if you know that x minus 2 is a factor, then you can proceed to go. We'll be getting to how to follow up on this in a minute. Then find the remaining factors. So how can you show that x minus 2 is a factor? There's two methods. You tell me what you want to do. Any ideas? Show that that is a factor of that. Help me, help me. Anybody? Say again? Synthetic division, what will you divide? Two on the outside. 2, 7, negative 4, negative 27, negative 18. Then you do what? Skip a line, draw a line, bring down the 2. Let's see what happens. 4, 11, 22, 18, 36, 9, 18, 0. What does that tell you? Yes, that x minus 2 was a factor because x equal 2 is a root, a 0, a solution. Okay? How about x plus 3? Do you have to start over and put a 3 on the outside and do it again? Here's the beauty, well, another nice thing about synthetic division. If that was a 0 there, and it is, then take this one and divide by, say again? Negative 3. And then you skip a line, draw a line, because guess what? If x minus 2 is a factor of this thing, then this remainder, this quotient, is also a factor of that thing. And if that's a factor, and x plus 3 is a factor, then that has to be a factor of this as well. So what do you do first? Bring down the 2, negative 6, 5, negative 15, 3, negative 9, 0. Sure enough, that's a factor too. All right. What does that 2, 5, and 3 represent? No, the remainder is 0. What does 2, 5, and 3 represent? Second? A little louder. What do we call this? Synthetic division. And what's the answer in division? Quotient. That's your quotient. So 2, 5, and 3, we need to put something else in there. What do we take out of there to put the 2, 7, negative 4, negative 3? The x's. So you put them back in here. What x's you put in? Say again? I'm sorry. Those are your coefficients of 2, x. See, you had a fourth. When you divided once, you got third. Once more, you got second. X squared. Go on. Plus 5x plus 3. And if we're looking for remaining factors, take this and factor it. If we can we? Now, if we can't, we can always use what? If factoring doesn't work, how soon we forget? Quadratic formula, of course, okay? Now, can we factor that? What would be the only possible factorization for 2x squared? 2x times x. Where do we look next? Sign of the last term. What is it? Plus. What does that tell you about these two signs? Got to be the same. What do they have to be? Both pluses, because the middle sign is plus. Okay, what's the only possible factorization for 3? Say again? 1 and 3. Okay, let's try it. Let's see if that works. Okay. 2x times x is 2x squared plus 6x plus x is 7x. That doesn't work. Wrong number. So what do we try? Changing numbers. If it was wrong sign, change signs. Wouldn't do any good here. But wrong number, we change numbers. So we'll swap, put the 3 there and the 1 there. Okay, 3 here, 1 there. Now let's try it again. 2x times x, 2x squared, that works. 2x plus 3x is 5x plus 3, yes it works. We found the remaining factors, okay? Now, here's a clue. We'll be doing this later. When you have these big old high-powered polynomials that are very hard, if not impossible to factor, the trisynthetic divisions, if you can get zeros as remainders, you know you found the factor, but don't go past 3 numbers here. Because once you get 3 numbers, that represents a quadratic. If it's factorable, you can factor it. If not, you can use quadratic formula. But anytime you got 5, 4, 7, 8, any kind of numbers up there, keep doing the synthetic division until you get down to 3, and then try to factor it. Okay, does that make sense? We found the remaining factors. Let's see how they did it. Can I erase this? Okay. So we did synthetic division with, if we're checking to see if x minus 2 is a factor, that would mean x equal to would be a root. So we put the 2 out here, skip a line, draw a line, bring down the 2. 2 times 2 is 4. 7 and 4 is 11. 2 times 11 is 22. Negative 4 plus 22 is 18. 2 times 18 is 36. Minus 27 plus 36 is 9. 2 times 9 is 18. Minus 18 plus 18 is 0. So that means that the remainder is 0. So therefore, x minus 2 was a factor. Okay? X equal to is a root. X minus 2 is a factor. Now, with that we had left over, don't go back to the beginning. Use your 3 into that. So when you do x plus 3 being a factor, if it was, that means x equal negative 3 would be a root. So put negative 3 out here, skip a line, draw a line, bring down the 2. Negative 3 times 2 is negative 6. 11 minus 6 is 5. Negative 3 times 5 is minus 15. 18 minus 15 is 3. Negative 3 times 3 is negative 9. 9 minus 9 is 0. Okay? So that's also a root. X plus 3 is a factor. Okay?
I have a question.
Yes.
How do you know to put x squared to x and then no variable?
Okay.
Do you always start with no variable and then work your way up?
Okay. Yeah, let's go back here. How did we get these numbers here? Yeah. We started with the polynomial, threw away the variable, and just put the coefficients in. Okay? And this was our dividend. That was our divisor. This is our quotient. That's our remainder. This represents, if put those back in then, 2x cubed plus 11x squared plus 18x plus 9. Okay? That's what that represents. Because every time you divide this into that, you drop one power, right? So that would be, this represents x cubed, x squared, x, and your constant. When you do it again, it started x cubed, now it goes to x squared, x constant. So that's where you took them out to begin with, you put them back at the end.
So you couldn't do it again to keep going.
You could, okay? In fact, since we know what one of those roots is x plus 1, right? So you could do a minus 1 on the outside. And let's do it. Let's just see if it works. Let's put a minus 1 here. It's not the best way, but you can do it. Skip a line, draw a line. Bring down the 2. Second. Negative 2. 3. Negative 3. 0. What's your remaining factor? 2x plus 3. So you could do it one more time. And that's easy, but when you get down to that stage, you can do it. Now, was there anything you could put here to make that work? This isn't synthetic division form because you have a coefficient of 2. If you had set this equal to 0, it is a factor, okay? Then subtract 3, divide by 2, you could have put a negative 3/2 in there, and that would work too, okay? So that's what you do if you have a coefficient, set it equal to 0, solve for x, and then put that number in. Let's go back up to this one and put a negative 3/2 in there into 2, 11, 18, and 9. That's what we had there. Let's see if it works. Bring down a 2, negative 3/2 times 2. Times 2. The 2's cancel out. Negative 3. Add. Add 8. Okay. Negative 3/2 times 8. Negative 12. Excellent. Okay. Add 6. Negative 3/2 times 6. Negative 9. See, that works too. 0. So x equal negative 3/2 is a 0. And then add that to both sides. X plus 3/2 would be a factor equals 0. And then multiply by 2. So that works too. We'll see that later. Okay? Any more questions? Good questions, by the way. All right. I don't think there's anything else they need to do on this slide. Let me erase the ink just to see. Yes, because the resulting is a quadratic expression, this, it can then be factored if it's factorable, and sure enough, that's what we got. So the complete factorization of that very first quartic polynomial is x minus 2 times x plus 3 times 2x plus 3 times x plus 1. You factored it completely. We will be doing this by the end of the next 2 sections. Okay, we'll be able to factor polynomials no matter how big and hairy and ugly and messy they look. We can factor them most of the time. All right, the jar ends here. Does anyone else come in since I called roll? I've been yakking at the board. I may have missed. Okay. All right, that was example 6. That's the last slide in the section. There is a little summary here. There's a checkpoint. I would definitely do that checkpoint. There's a summary here, and by the way, you can see those. They actually graphed that solution to that big hairy polynomial we had. And in fact, let's go back and look at that. They didn't show the graph. Here's our polynomial. What can you tell me about the graph of this polynomial? Tell me everything you can think of about the graph of that. Start with going in the same direction because that is even. What direction is it going? Up, because that's positive. Okay, sure enough. So it's on the up and up. Look at the picture in your text. Sure enough, it's on the up and up. Okay? Let's see. Anything else we can tell just by looking at that? Oh, how many possible zeros do you have? 4. Exactly, because the maximum degree is 4. How many factors did we wind up having? 4. So those are our 4 zeros. X equal 2, x equal minus 3, x equal minus 3 halves, and x equal minus 1. Well, let's go, look at the graph, and there's x equal minus 3, x equal minus 1, x equal minus 3 halves, x equal minus 1, and x equal 2. Sure enough, there are our zeros. How many turning points did you expect from this one? 3, up to 3. Let's see at the graph. You have 1 there, 1 in there, 1 down there. Sure enough, you had 3 turning points. You may not have 3, but you could have up to 3. You met it. Okay? Anything else we can look at that and see? I think not. All those zeros were, all the factors are to the first power, so that means the function crosses the x-axis at each of those points. Doesn't go far at x equal negative 3 halves because it turns right around and comes back down to x equal negative 1, but it does cross. And notice the function is all positive outside that first one, all negative between the first 2, slightly positive between the next 2, all negative between the next 2, and then all positive beyond. Yeah. So lots of things we can tell about the graph just by looking at the function. All right, let's now do our vocabulary, your favorite parts, right? 2 forms of the division algorithm are shown below. Identify and label each term and function. So I'm going to back up, okay, and write them here. Here's one form of your division algorithm. F of x is equal to d of x times q of x plus r of x. Okay, and the second one is f of x divided by d of x is equal to q of x plus, what would be the last? R of x divided by d of x. Okay? Now, what they ask you to do, identify and label each term or function. What is this called? F of x in both cases. That's your major function, also given the title, the dividend. Okay? What is d of x? Both ways. Divisor. What's your q of x? Quotient, and r of x, remainder. And every one there named the same. Okay, that was pretty easy. All right, exercises 2 through 6, fill in the blanks. In the division algorithm, the rational expression r of x over d of x, on that last one, is blank because the degree of r of x must be less than the degree of d of x. What do we call that? Any ideas? Fractions are either... Yes, and which is this? Proper, because the degree of the numerator is less than the degree of the denominator. Number 3, in the division algorithm, the rational expression f of x divided by d of x is blank because the degree of f of x is greater than or equal to the degree of d of x. Improper. Yeah, very good. Number 4, an alternative method to long division of polynomials is called blank blank, synthetic division, in which the divisor must be of the form x minus k. Okay? In other words, coefficient of 1, exponent of 1. Number 5, the blank theorem states that a polynomial f of x has a factor x minus k if and only if f of k is equal to 0. Factor theorem. And number 6, the blank theorem states that if a polynomial f of x is divided by x minus k, then the remainder is r is equal to f of k. Remainder theorem. Okay, very good. Homework exercises. Do number 7, do number 9, do any of the odds 11 through 25, and do several of those. Then do any of the odds 27 through 35, and then do any of the odds 37 through 45. Okay? Then do any of the odds 47 to 53. I think these are new ones. Do either 55 or 57, or both. There's 4 parts to each of those, by the way. Using the factor theorem, do any of the odds 59 through 65. And do either any of the odds 67 to 73. Do any of the odds 75 to 79. And do either 81 or 83, or both if you choose. And then there's an application problem, number 85. I would try to do that one as well. There are some exploration, 2 true false, odd 2 false anyway. Do those and then look at 91, 93, 95, 97. Think through those as you do it. All right, now. Okay. We are probably a little bit behind where I would like to be. I'm definitely behind. And 2.4 talks about complex numbers. Now, in the course description that says what we have to cover in this course, complex numbers wasn't mentioned, okay? And it's not saying they're not important, but it probably means you'll run into them. When you run into them, you'll deal with them then. So what I'm going to do here is just do a slideshow in 2.4, okay? Just so you'll be exposed to them, but I'm not going to hold you responsible for them on tests and stuff. Oh, and by the way, before you leave today, pick up your quiz, because we do have the quiz. I'm pretty sure she got it copied. Let me make sure. I know I put it in the box. I've graded everything you've turned in. Were you through with it? Oh, okay. Well, then see me right after class. I'll put the grade on the book, because I didn't want to put the grades down until I was sure you were through. Okay, let me see. Test. Yes, I've got the quizzes, so don't leave the room without them. Now, I may not have run off enough graph sheets. I have some, but if you need more graph sheets, I'll run those off too. Or you can wait till next week and just not do the graphing yet. Okay, so don't leave without your quiz. I don't want you having the whole weekend and thinking, oh, I wish I had that quiz to work on, you know. So please take it before you go. All right, the objectives here, which we're not going to do in great detail, use imaginary unit I to write complex numbers. Add, subtract, and multiply complex numbers. I'll show you how to do it. You're not going to be responsible for it. Use complex conjugates to write the quotient of 2 complex numbers in standard form. That's, again, you're not required to do it, but it's a nice thing to know if you ever run into it. And we'll find complex solutions for quadratic equations. We'll just hit that. Let's start with the imaginary unit I. Anyone know what that is? Okay. Now, you've learned that some quadratic equations have no real solution. For instance, this one. X squared plus 1 equals 0. Can you give me an x that makes that true? No, because any x in the real number system that you square it, it's going to be positive. You square a positive number, it's positive. Square a negative number, it's positive. So you add a positive to 1, it's still positive, okay? Even if the x was 0, 0 plus 1 is positive. So how can you get a 0 there? You really can't, okay? Let me find you in the book. Courtney, right? Yeah. I have trouble seeing with the light in my eye here. Okay. All right. So this has no real solutions. Does that mean it has no solutions? It has no real solutions, no real number that can be used. But to overcome that deficiency, mathematicians way back created an expanded system of numbers. And let's back off a little bit. Way back when you were in maybe kindergarten or grade school, what numbers did you always play with first? Yes, the counting numbers. Those you used to count with, 1 through 10, then you went up to 20 and 50 and 100 and all like that. You just counted with the numbers. And that was enough for a while. But then at some point, and we called that system the counting numbers or the natural numbers. Set of those numbers, all those numbers you can count with, goes to infinity, okay? But they're all whole numbers. Okay, I used the wrong word there. Counting numbers. Natural numbers are counting numbers. Then we added one simple little number to that set, 0, and now that's the whole number system. Still infinite that way, but now it ends at 0 rather than starting at 1. Okay? And then after a while, and this isn't the order you probably learned it, but it's after a while, you took the negative of those numbers. And that made up the set we called, no, those are integers. Remember, we still don't have fractions or decimals, okay? Integers. Positive numbers and negative numbers, but always the counting numbers. Then, when we divided by some of those integers, we had rational numbers, okay? And those were fractions and decimals. Decimals that repeated or were terminated, okay? So that gave us the rational number system. But not all real numbers are rational. Square root of 2 is not rational. Square root of 3 is not rational. Square root of 5 is not rational. Square root of 6, square root of 7, square root of 8, square root of 10, square root of 11. Yeah, lots of numbers. E, pi, lots of numbers are not rational. Okay? So therefore we add rational numbers and irrational numbers. Now when you added those two together, you had what we call the real number system. That was every point on the number line. Every one. The fractional point, the irrational points, every point on the number line could be represented by a real number. Okay? But now we introduce imaginary numbers. Okay? To overcome that deficiency, mathematicians created an expanded system of numbers, and this new system is called the complex number system. It includes all the real numbers plus those with imaginary components. And here's that imaginary unit I. If you were to try to solve this equation, subtract 1 from both sides, then you have x squared is equal to negative 1, right? Then you take the square root of both sides, x is equal to the square root of negative 1. There's no real number that makes that true. So they make up this number, an imaginary number, and say that's the square root of negative 1. Okay? Now, what else is true about that? What would happen if you squared both sides of this equation? That would be I squared. This would be negative 1. So these are the two things to know about the imaginary unit. That stands for the square root of negative 1, and I squared is equal to negative 1. Only number in the world that will be, you square it and you get a negative 1. Okay. It's imaginary, not real. Okay. So by adding all the real numbers and then combinations of this imaginary unit, now we have the set of complex numbers. Each complex number can be written in standard form, a plus bi. Okay? The a's and the b's are both real numbers. But the b is multiplied by your imaginary unit. So that makes this a real part, that's an imaginary part. For instance, the standard form of the complex number, negative 5 plus square root of negative 9. Now, that's not a real number. Square root of negative 9 is not. Negative 5 is a real number. So what you do here is split that using the rules for radicals, okay? And you can split that to be square root of negative 1 times the square root of 9, right? Negative 9 is negative 1 times 9. Well, what's the square root of 9? 3. Square root of negative 1? I. Okay. I. So that would be negative 5 plus 3i. There's your complex number that is that value. Not a real number, but a complex number. Okay? And they did the same thing I did. Plus 3i. Okay. Any questions on that? So here's the definition of a complex number. If a and b are both real numbers, then the number a plus bi is called a complex number. And it is said to be written in standard form. Always the real part first, the imaginary part second. The real number a is called the real part, and the real number b, I don't like this terminology. They say the real number b is called the imaginary part. I like to say bi is the imaginary part. This book uses a slightly different definition than what I'm used to. When b is equal to 0, though, guess what you got? A real number. So all real numbers are complex numbers, okay? But not all complex numbers are real numbers, okay? When b is equal to 0, that a plus bi is a real number. When b is not equal to 0, then you have a, they call that an imaginary number, okay? Which is fine, that's exactly what it is. And when a is equal to 0, but b is not, that part bi is called a pure imaginary number with no real part. So when b is equal to 0, you have a real number. When a is equal to 0, you have a pure imaginary number. Okay. A plus bi, though, is an imaginary number or a complex number with imaginary part. Okay. So here's how you show it in a diagram. Real number system. Set of all numbers, remember, they are positive, negative, fractions, decimal, rational, or irrational. That makes up the real number system. The imaginary numbers are those that have components with I in them. And together they make the complex numbers. So all real numbers are complex numbers, but not all complex numbers are real. This is true because every real number can be written as a complex number with b is equal to 0. That is, for every real number a, you can write it as a plus 0i. But why would you want to? Okay. Now, what do we mean by two complex numbers being equal? For a plus bi and c plus di to be equal, that means that real parts have to be identically the same, and the imaginary parts have to be identically the same. A is equal to c, b is equal to d. Now, say identically the same value, okay? If this were 3 plus 4i, and this was 3 plus 8 halves I, those are the same. 4 is equal to 8 halves, okay? So yeah, as long as the values are the same. If a is equal to c and b is equal to d. Okay. Operations with complex numbers. Adding and subtracting, easy, okay? Add or subtract complex numbers for two complex numbers, a plus bi, c plus di, to be added together. They're written in standard form. You add the real parts, a plus c, a plus c, and then add the imaginary parts, b plus d times I. Okay? Just like I hope you would expect it to be. Here's how I think of these. Think of them as terms. You add like terms, you subtract like terms. So the same thing here, you add real parts, you add imaginary parts. Think of them as terms. If you're taking a difference, a plus bi minus c plus di, then you take a minus c plus b minus d times I. Add or subtract the real parts, subtract the imaginary parts, and add those together. All right. Now, additive identity and complex number is still 0, okay? It's a 0 plus 0i. If you want to say it that way, but that's still just 0. Furthermore, the additive inverse of a complex number, a plus bi, would be minus a minus bi, which is exactly this. It's just the opposite of this. And again, treat it as if it was a binomial. When you negate a binomial, negate each term of that binomial. That's your additive inverse. Now, it's also true that if you add a number, a complex number, to its additive inverse, you add a minus a, that gives you 0. B minus b, that gives you 0. So you have 0 plus 0i, which is simply 0. That's what the additive inverse does. You add it to itself, its inverse, and you get 0. Now, I'm not going to take the time unless you want to do them of how to actually add these. But, I mean, you can just look at it and see. 4 plus 1 is real parts. 5. Second. Minus I. Okay, you don't have to put the 1. I mean plus I. I'm sorry. 5 plus I. Okay. Sure enough, that's your answer. Well, they'll get to it. Yeah, 5 plus I. Okay. How about this one? 4. Yeah, 0 I. Okay, right? So it's 4. Okay. So you can add 2 imaginary numbers together and get a real number if the imaginary parts add to 0. And indeed, that's what happens here. Okay? How about this one? Start with the real parts. Minus a minus is plus 2. Minus 2, that's going to add to 0. No real part. Here we have a 3i minus 3i, that adds to 0, and this is a minus 5i, so your answer is minus 5i. After they do all they do, minus 5i. So you can have 2 or 3 complex numbers adding together, and even though some of them had real parts, your answer may be pure imaginary. Okay? How about this one? Okay, you got several things to do here. Let's just take the real parts first, just like terms. 3 plus 4 minus 7, that part's 0. 2i minus I would be I. That means yes in the Navy. Okay, no problem. Minus I is 0. This adds to 0. Let's see if they got it. Yes, adds to 0. Pretty easy to add or subtract complex numbers. Now, many other properties of real numbers are valid for complex numbers as well. Associative property of addition and multiplication, commutative property of addition, multiplication, distributive property of multiplication over addition. Everything you do in the real number system, pretty much you do in the complex number system. I can't think of anything that's changed. Okay? And then when you're multiplying complex numbers, guess how we do that? Just like multiplying 2 binomials. What technique do we call that? Curses. Fold again. Okay, never mind. That's the old Rocky and Bullwinkle thing. Y'all wouldn't remember that. Okay. You do first, outer, inner, last. But there's something special here. Okay? And here's what it is. When you do the first, that's obviously real, right? A times C is a real number. Those are both real numbers. They're real numbers. When you do A times DI, that's the outer, and B times BI times C, those are both imaginary parts. Okay? So ADI plus BCI, that's an imaginary part. But look what happens when you get to the last. BI times DI, what does that give you? times D, real. I times I is I squared. And what is I squared? Negative 1. So suddenly that goes real too. Your first terms are real, the innards and outers are imaginary, but the last become real. They just change the sign. That would be a minus b times b, because I squared is minus 1. And they're going to get to that right here. So you have AC minus BD is the real part, and ADI plus BCI, that's your imaginary part. Okay? So don't memorize that. Just FOIL it. You only have 2 every time, so just FOIL it. Okay? Or multiply it. Okay? Let's do a distributive law here. It's pretty easy. What would this be? Negative 8 plus 12i. That's all. That's it. Can't make it any harder. Wish I could. I've tried, but I can't make it any harder. How about this one? Now this one you got complex, okay? So what do? First is 8. Let's jump to the last now. That would be again. What would that be? Last times last. Negative 3i squared. What's I squared? So negative 1, so that would be plus 3. 8 plus 3 is 11. That's your real part. What's your imaginary part? Outer. 6i. Inner. Negative 4i. 6i minus 4i is 2i. So that would be, what did we say it was? 8 plus 3, that's 11 plus 2i. Okay? Let's see what they got. There we go. 11 plus 2i. That's how you multiply complex numbers. Okay? How about this one? 9. Go to your last and you get? Second? Last. Negative 4i squared. So I squared is? So that would be positive 4, right? 9 plus 4 is 13. There's your real part. What happens to the imaginary parts? Outer, negative 6i, inner. What does that add to? 0. What has just happened? You multiply 2 complex numbers together, you get a real answer. Only real. That is important. And by the way, what do we call these 2 numbers? How do they look similar or different? Isn't that a little like a plus b times a minus b? That gave us a squared minus b squared, right? In complex numbers, it gives us a squared plus b squared with no cross terms in it. These are called conjugates of each other. When the numbers are the same, but the signs are different, one sign is different, you call those conjugates. Since these are complex numbers, we call them complex conjugates of each other. Okay? So they get 9 plus 4, 13. You just multiply the reals, multiply the imaginary, change the sign of the imaginary, and you get 13. So that's how you can change a complex number into a real number multiplied by its conjugate every time. Okay, what happens if you square a complex number? What do you reckon that's going to give you? Well, take it apart and FOIL it. What do you have? 9 minus 4 is 5. That's that part. This is 6i plus 6i would be 12i. It's just like you did before. Square the first, square the second, twice the product in between. Same thing here, except when you square the second, you get a minus. Okay, minus I for I squared. Minus 1 for I squared. So that gave us 9 minus 4, that was 5, plus 12i squared. 12i. Okay, we'll get to it. 5 plus 12i. Good deal. All right. Introduce complex conjugates. This is what they are. How are we doing on time? 3 minutes? All right, let's see how far we can get. Notice that in example 2c, the product of two complex numbers can be a real number if and only if they're complex conjugates of each other. One part's the same, the other is identical except for the sign. That is a complex conjugate. And the answer to this every time when you multiply a complex number by its conjugate, you get the sum of their pieces, sum squared, okay? Every time, okay? All right. I wanted to go and finish this. Let's just do. Here's a hint. Here's where we use complex conjugates. When you're trying to divide complex numbers, really difficult to do. Because how do you divide an imaginary thing into something? I don't know. So what you do, multiply the denominator by its complex conjugate. That's going to make the denominator real. But if you multiply the denominator by a complex conjugate, you multiply that number times your numerator. That's going to get you a complex number, but you're dividing by a real number. Okay? That we can do. We can always divide by real numbers. Okay? And here's some examples. I won't go over it. You can look at them in the book. And here's the key, though. And the book always does this. When you carry this out, your denominator always turns out being a real number, but then split them into real and complex parts. Okay, real and imaginary parts. That would be 2 over 20, which is 1 over 10, plus 16i over 20, which would be 4/5 I. So I always write it in standard form, real part, complex part. Split that denominator and use them under both. All right, we won't go into this. If you need to know it, you can go back and do it. We've done that already before, so we'll take that out. So don't sweat this. You can go and look at it. Remember, in our quadratic formula, if you got a negative here, we had no real solutions. That means they had complex solutions, and then carry that on out. Okay? I won't go any further. All right, next time we will start with 2.5. 2.5 we will cover. We'll skip any part of 2.5 that has complex parts in it, but every other part is pretty important. Now, don't leave without your quiz. Did anyone get out the door? Okay. Let me give you your quiz. And let me also ask you if you need graph paper. Okay. Who wants first? Need graph paper? You don't need graph paper, okay? All right. Here's the quiz. Need graph paper? Quiz. Need graph paper? No? Quiz. Need graph paper? Need graph paper? No? Whoa, wait, that's not it. Did I give you a quiz? The last one? Yeah, that's right. Where is my quiz? Oh, here we go. I hope I gave you the right quiz. Somehow they got separated. Wait a minute. That's one. Quiz. I know I had these copied. Where are they? I'm going to have to go find them. I looked and saw that bunch of them and thought, okay. I had them turned in yesterday. Let me see. You may have put them in a different location. Be right back. by this morning. I thought work says to do that, pick it up, but yeah. If you need graph paper, let me know. Okay. Quiz, graph paper? No. Graph paper? Graph paper? Graph paper? Graph paper? Yeah, that's great. Graphless class, graph paper? Graph paper? Okay. You get one too? Okay, there you go. Graph paper? Yes? Okay. Graph paper? Okay, sorry to hold you up. I thought she had already got it. But, oh yeah. Oh yeah, who else was asking about the test? Yeah. And what about yours?
I'm done with it.
You're done with it. Let me make sure you see your grades so before I put it in the book. It's not bad, it's good. Well, I don't know. 63. You want to try to do any more? Cause you left 2 blank at the end. Huh? Take the 63? Okay. Okay. All right, and it was Diamond, the other one, wasn't it?